Okay, so now we're going to take a look at selection, which is another very important component to understanding evolution. And we're going to assume that we have X individuals of a given type and Y individuals of another type. Okay, so now we have a population that's made up of two types of individuals, and at time t there's X of the first type and Y of the second type. And we're going to have dx dt equals ax, and dy dt equals by. Okay, so now this is not terribly interesting, because now what we've just done is taken the previous problem of reproduction and just said now you got twice as many, well, two things reproducing. So that's not terribly interesting, but what does become interesting is, okay, maybe they're both taking over their environments, but if they have a shared environment, what's the ratio? So if we say, well, let's consider rho of t to be x of t over y of t, right? So a row of 1 means they share the environment, a row of 0, well, a row tending to infinity or to 0 makes this tells us what's happening over time. So we can just calculate the derivative of rho with respect to t using basic rules of calculus. So that's just going to be dx dt times y minus dy dt times x over y squared. And that's given by xy a minus b y squared. And this is me just substituting things in. And we can just pull out that that's actually x over y times a minus b. That, of course, x over y is just rho times a minus b. And so now we have that rho of t is equal to rho naught e to the a minus b t, where rho naught is just rho at time t equals 0. And so now we have that this is an exponential curve that either increases or decreases. And basically, if the first type grows faster than reproduces faster than the second type, they will take over, and if the second type reproduces faster, they will take over. So nothing too interesting there, but this is the basis for selection. Things are going to start to get interesting when we constrain this somewhat.